Okay, so we'll finish this off with a discussion of now symmetric matrices. And a symmetric matrix is just a square matrix which satisfies the condition that it's equal to its transpose. So if you take a matrix A that's square and you take its transpose and you get itself back, really you just now you're talking about a symmetric matrix. So that's what it means for a square matrix A to be symmetric. Okay, so just some examples. Here's a 2 by 2 matrix. This is symmetric, right? If I took the transpose of this matrix, I would get exactly this matrix. Here's another way to think about it, right? The first row is equal to the first column in terms of what the entries are. The second row is equal to the second column. The second row is negative 3, 7. Second column is negative 3, 7, right? First row is 7, negative 3. First column is 7, negative 3, right? If you just say the entries out loud and they sound the same for the first row in the first column and the second row in the second column, then that's what it means for this matrix to be symmetric. If you want to think about it in terms of symmetry, you could think about it as a mirror image across the main diagonal. Like the main diagonal can be absolutely anything else, the main diagonal could be absolutely anything, but if you take two entries that are reflections of each other, in terms of if their positions are reflections of each other across the main diagonal, then the entries better be the same. So in this case, they're both negative 3 and negative 3. So it's almost like the middle diagonal acts as a mirror. Okay, and that's what you're looking for. Like this one, for example, the main diagonal is 1, negative 3, and 7. But this corner up here is a mirror of this corner up here, right? The 4 and the 4 match up, the 5 and the 5 match up, and the 0 and the 0 match up. So you can think about it that way as well. But officially, it's just if it's equal to its transpose. That's what it comes down to. So the first row, 1, 4, 5. First column is 1, 4, 5. Second row, 4, negative 3, 0. Second column, 4, negative 3, 0. Right? They're the same entries. The third row is the same entries as the third column. That's what you're really looking for. Okay, so this is another example of a symmetric matrix. Now this, what have I got here? And diag D1, D2, D3, and D4. What am I talking about here? Well, this is the diagonal matrix. It's a 4 by 4 diagonal matrix with D1, D2, D3, and D4 on the main diagonal. Well, what are D1, D2, and D3, and D4? I didn't tell you. Well, it turns out, let me change this to a comma. It turns out that this is an example of a symmetric matrix no matter what the entries D1, D2, D3, and D4 are. No matter what's on the main diagonal, a diagonal matrix is always symmetric. So let's finish this off by saying for any real numbers D1, D2, D3, and D4. Okay, so that's guaranteed to be a symmetric matrix. In fact, any diagonal matrix, no matter how big or small it is going to be a symmetric matrix. And you can write one down to convince yourself of that. Okay, the last thing we're going to discuss is now a theorem, which just makes some statements about symmetric matrices. Some of them are obvious and some of them are not obvious. Okay, so theorem. The first one says that if A and B are symmetric matrices of the same size, and K is any scalar, then, well, there's 5 statements that we're going to write down. And the first one, you almost would think that it's not even worth writing down. Once you think about it the right way, it almost seems silly to even say it, but nonetheless, we're going to say it. If you know in advance that A and B are symmetric matrices, in particular, A is symmetric, well, then it turns out that A transpose is also symmetric. And why is that? Well, because A transpose is equal to A. So there's not much of a mystery there, right? It's almost so self-evident you wouldn't even write it down. But no, nonetheless, we'll still write it down. The next thing we'll say, these ones have a little more substance to them. A plus B and A minus B are also symmetric. Right? That's under the assumption that both A and B were already known to be symmetric, and of course they were the same size. Why do we need them to be the same size? So that these two expressions are defined. Right? So if A and B are symmetric and you add them together, the result is going to be symmetric. If you subtract them, the result is going to be symmetric. Okay, the third statement says that this scalar here, we're going to use this scalar now, if you take the matrix A and you multiply it by the scalar k, well, the result is now, again, a symmetric matrix. Okay, so that's the third statement. Now, the fourth statement is a statement about the product. AB is symmetric, and I'm actually not going to put a period here just yet because it's not quite that simple. So it would be nice if we could just say AB is symmetric. That would mean the product of symmetric matrices is symmetric, but it turns out that's not always going to be the case. But sometimes it will be. But what this statement is going to give us is a criterion to determine whether AB, the product AB, is symmetric, just based on properties that A and B have. So the product AB is symmetric if and only if A and B commute. And I haven't told you what that word means yet, and I'm going to tell you right now. So what does it mean for two matrices, A and B, to commute? So that is, in other words, their products are the same no matter which order you multiply them in. Okay, that's certainly not true for any matrices A and B, but for matrices A and B such that this equation is true, we say that those two matrices commute. So if these two matrices A and B commute, then the product AB is symmetric. But if they don't commute, in other words, if this equation were to fail, then AB is not going to be symmetric. That's what statement 4 is saying. Okay, and statement 5 says that if A is invertible, then, and again, we're still under the assumption that A and B are both symmetric matrices. So if A is invertible, then it's invertible and symmetric, and its inverse is also symmetric. So that's what our statement's going to be. We'll say if A is invertible, then A inverse, oops, I messed that up. I meant to write it as symmetric. That's a bummer. I'll scratch that out totally so it's obvious that that's a mistake. So if A is invertible, then A inverse is symmetric. And note that this would be something that's really easy to read out of context. If you don't pay close attention to the context, it's easy to misinterpret this as a false statement. It almost sounds like I'm saying that the inverse of any invertible matrix is symmetric. Like if I were to cover all this up and you didn't read what came above this, you didn't read the context, which was that we have two matrices A and B which are both already known to be symmetric. Right? If we didn't include that, then this statement wouldn't be true. Right? So you have to read it with this context. So really what this statement is saying is that if you have an invertible symmetric matrix, then A inverse, which you know you have because we just said if the matrix is invertible and symmetric, then A inverse is also symmetric. That's what this statement is saying.